als Tour, es ist eine Tour.
Good morning, everyone. It's a pleasure to introduce today's speaker, Samuel Brieden. So Samuel is at the moment a postdoctoral researcher at the University of Edinburgh in the group of Florian Butler. Before then, he was a PhD student in Barcelona, supervised by Elisha Verde. And before then, he started already to work on cosmology during his master in Aachen with Julien Lesbourg. And he worked a lot on the analysis of data from galaxy surveys. In particular, during his PhD, developed a method to extract information from the shape of the power spectrum. And at the moment, he's actually involved in the DESI collaboration, as you can guess from this very cool T-shirt. And he will tell us about from the precision era toward the accuracy era of cosmology with DESI. Thanks a lot. The stage is yours.
Yeah, thank you very much for the introduction, and thank you for the invitation. It's a pleasure to be here today and yeah, give you this talk on how I already heard from the audience, the bold title of From the Precision Era Towards the Accuracy Era of Cosmology with DESI. And yeah, let's focus on that title a little bit for the beginning. So I know that every one of you is aware of what's the difference between precision and accuracy. So imagine that I throw darts or arrows into the sky. If I'm accurate and precise, I will always hit the bullseye, right? I can also be accurate, but not precise, which means I have a large, I'm still hitting the bullseye, but with small precision. I can be neither accurate nor precise. That's how it looks like. I can be very precise, but not accurate, because I always hit in the same area, but not the truth, the bullseye. But in the end, we always want to be both accurate and precise when we do measurements and say something about physics. So you have probably heard about this term precision era of cosmology. For those of you who don't, probably you still have the prejudice that cosmology is actually more an order of magnitude science. So whether cosmologists would say, assume pi is 1 or 10, whatever. But actually, this is not true anymore. And we have heralded this precision era of cosmology since the advent of the cosmic microwave background radiation, which is the first radiation we got to see from the universe, because it was the radiation emitted once the universe has cooled down sufficiently such that neutral atoms were formed. So protons and electrons recombined, which allowed photons to have a free path and propagate freely. So the universe really made a phase transition from being opaque towards being transparent. And that radiation was measured by COBE in 1992. And they made a very high precision measurement of the photon CMB temperature up to, 4 digits, a very precise measurement of the temperature. And that was even topped by the experiments that came afterwards, the satellite experiment WMAP, which measured for the first time, or COBE also already measured them, but really with high precision, W measured that the fluctuation of the temperature is of order 10 to the minus 5. So there are really tiny fluctuations depending on which area you look at in the sky. And this was even the legacy. Now we have the Planck legacy, where we really have a very precise map and a very precise spectrum of, depending on the angular scale we look at, what's the fluctuation amplitude. And we see this beautiful pattern here that I will comment on in more detail later. And I also looked on the archive, like when was this term precision era for the first time used in cosmology? And actually, if you look at the first reference by Wayne Pugh in his PhD thesis, I think, where he said that with COBE, we have now entered the era of precision cosmology. On the other hand, if you look for accurate cosmology or the era of accurate cosmology, there are just a few there are not, by far, not as many references. The first one is by Peebles, who mentioned the title From Precision Cosmology to Accurate Cosmology. And then there was a title by Licia Verde, Precision Cosmology, Accuracy Cosmology. But you can count it on one hand. So I asked myself, why is this the case? Why do we focus so much on precision and not on accuracy? And I think think about it a bit, claiming precision is actually relatively easy. You can just say, look, it's easy to convince yourself that you have a small statistical error and that you can obtain tight constraints on model parameters. And that's it, you have precision, right? If you are claiming accuracy, you're actually doing something very bold. You claim that you have a small systematic error, which you actually cannot, because the systematics we always know that there might be unknown unknowns. So how do you say, I know there are no unknown unknowns? It sort of doesn't make sense, right? And you say that your model is a good description of reality, which we know that our models are a very good description of reality, but they are we never really reach the absolute truth. And it's really an ongoing process to get to the truth if we get there in any case. So claiming accuracy is very hard or bold. So in this talk, I would like to convince you first that we are indeed in the precision era of cosmology. And I give you a perspective on what is my perspective on how we can obtain closer to accuracy. We will never be able to claim absolute accuracy. That's not how science works. But we can argue why we think we have more accurate means of describing the reality than probably we would previously. So to go back to the cosmic microwave background and this beautiful power spectrum, I show this video by Isa telling us how we can decompose the sky in different angular scales and just measure the amplitude given the different scales. So for example, you have the angular size of 0.5 degree, roughly corresponds to the angular size of the moon. We basically measure how strong are these fluctuations depending on the angular size. And you see this region here is roughly the size of the moon. And there we have this peak where the angular fluctuations are quite strong. And these are oscillatory. So there are some higher modes of that first peak. And so to understand this, I think it's really hard to appreciate why from this map we can learn so much about the universe. And I think the nicest analogy, the analogy I liked most to understand why we can actually have a precise notion of the universe is imagine the early universe like a miso soup. It's a quote by Eiichiro Komatsu, who was one of the main leaders of the WMAP mission. So yeah, I'm trying to explain why imagining the early universe as a miso soup is why that is precise. Okay, it's
without tofu.
with tofu.
With tofu.
So imagine you have a medium like the early universe, and the medium can have different compositions. These are two different boxes with two different composition of the medium, the ingredients of the medium of the early universe. Then you throw tofus into the medium. This is a single tofu, okay? And depending on the medium, the waves propagate in a different way. As you see here, they decay sooner or later, and the velocity of the medium of the wave will be different. So now in the reality, we have not only one tofu, we have a huge distribution of tofus. And they lead to a wave pattern. And what we basically try to do is we try to extract, given some initial distribution of tofus, how do the waves propagate? And given we have such a huge sky with the CMB, we can actually say a lot of detail about this, and we can simulate how this map would look like depending on the medium. And one one contribution that we can model, which is really good, is the bioacoustic oscillations, which are simply related to the fact that in the early universe, when the initial fluctuations came from quantum fluctuations, the waves only had the time from the Big Bang until the time that the photons decoupled from the medium and the photons were emitted to propagate. And for different models of the universe, we can simulate. On the left, you see one Gaussian initial condition that is spreading, okay? And on the right side, you see a more realistic realization of initial fluctuations that we expect from inflation, okay? So we call this distance that is traveled by wave, the sound horizon. We know that it's approximately 500 million light years, 150 megaparsec. And actually, probably it's hard to see now by eye, but if you look at this image, you can actually recognize that there is a characteristic distance that is described by the distance between, on average, high temperature and low temperature regions. And that's basically what we do to infer that distance from this map, from the data that we see here. And with this, by modeling how this fluid would evolve, we have a very good estimate of what's the cosmic recipe of the universe, what's the abundance of atoms with respect to dark matter, to dark energy. And to elaborate a bit more on this analogy, actually, I had a summer student last summer, and she made a soup animation. She expanded that animation I was showing before, which is incorporated in class in the cosmological parameter estimation code. And she basically made a soup bowl, and you could set the initial conditions and the ingredients of the miso soup and see how the waves propagate depending on the medium. And I also went ahead, I tried to make a picture when the miso decoupled from the miso soup and tried to see some oscillations there. And I saw something oscillating, so I was very happy. And I thought, wow, there's an oscillation. But then I asked myself, did I really measure the BRO in the soup bowl? Or did I confuse the BRO with the soup bowl? Because there's a ring pattern here, which is the bowl itself. I didn't think about this. So I took the bowl away. I still found something which is not as strong. But maybe it's just because there's a problem. Maybe the bowl is not big enough, and the waves, they scattered back and forth, then they just decayed. And exactly, the waves decay before the miso actually decouples from the soup, and the miso becomes transparent. The soup becomes transparent. So I think the problem is that I was basically only getting that part of the spectrum where everything has decayed. And we are fortunate enough that the universe is big enough, and the BO waves were not damped by the time it decoupled. Well, it could be other way. It could also be that they decayed already, but we are lucky enough that we can observe them. And since we can observe them, we can use them as a standard ruler. And that's very important to what I will talk about next, about the actual DESI measurements, that this scale is imprinted in the distribution of galaxies on large scales. And given that we know the distance, or if we have a model to describe the distance here, we can just check how does this distance change with the expanding universe, and we get a measurement of the expansion history of the universe. So that's the idea of this measurement. But before that, let me also talk a bit about the lambda CM model, our current understanding of the universe, the lambda CM model that we use to describe the universe. And I would say it's a bit simplistic image, but it relies on three very solid pillars. One, I would say, is the cosmological principle, which gives us the metric. If we assume that the universe is homogeneous and isotropic at all times, the only degree of freedom that we can add are space-time curvature, given by the scale factor A as a function of time. There's also spatial curvature. I don't talk about this now, and it wouldn't fit in the equation here if I put it, but there's also, you could also add spatial curvature in here in the metric term here. So this is one pillar. The next pillar is GR, general relativity, which this tells us, given that metric, given how space-time is looking like, how does it evolve given the matter content, the energy density of the universe in its different components. That's the Friedmann equation, which comes directly from the Einstein equation if we use that metric from the cosmological principle. And finally, the standard model of particle physics. So we know in the universe what is the universe composed of? It's all the stable particles, right? There's photons, gamma, neutrinos, electrons, protons, neutrons, and other nuclei. For simplicity, and now you would say, why do you say precision cosmology if you do this? I think it's really bold. We say all of this is baryons. Electrons, protons, neutrons, it's just baryons. Okay. Yeah, we don't care about leptons. That's precision cosmology. In addition to that, we have 3 ingredients of the model that are not as solid, let's put it in that way, which are inflation. We have to assume some initial conditions for the universe. Then we have this weird lambda term, the cosmological constant, which comes from Einstein equations, but we can also interpret it as if it was an ingredient of the universe itself, dark energy, which is something puzzling that we don't still yet understand. And we have the cold dark matter. And as you see, this makes up the term lambda CDM, is basically these 2 ingredients, which, as I said before, is 95% of the energy density content today. And baryons are only 5%. So we have this model. These are the parameters it depends on. So inflation gives us these 2 first parameters, which are the amplitude of the initial fluctuations and the tilt of the initial fluctuation, AS, and the tilt is NS, which tells us something about how perturbations are generated by quantum fluctuations and inflation. Then we have all the energy densities, so photons, neutrinos, baryons, cold dark matter, lambda. If they sum to 1, the universe is flat. If they don't, it's curved. And the Hubble expansion rate at today, which together with this then determines this equation. So how do we measure exactly all of these parameters? So again, we have the Big Bang at redshift infinity. We have the recombination at redshift 1089, and we have the formation of the first stars and galaxies at lower redshifts, and we are here at redshift 0. And basically the question I ask myself is, which of these parameters is actually directly measured and which is inferred assuming a model? Okay. So the CMB temperature is measured by COBE, and it gives us a direct estimate of the photon abundance. And with that, we can infer also the neutrino abundance if we assume how they are related after electron-positron annihilation, entropy conservation, and that gives us the relationship between the energy density of neutrinos and photons. Then we have the CMB anisotropies, which give us, we can infer a model, from that we can use a model and infer all of these parameters, but what we actually directly measure is this peak that I showed in the spectrum, where the location of the peak, the angle of the peak, it's also sometimes rephrased as the theta s parameter. And that's like a direct thing that we see from the data, okay? And we can, it's an alternative way of expressing the H0 parameter. Then we have BBN. We can measure the abundance of elements and infer the baryon density from that indirectly with using a model. We have the supernovae, which we can use as a standard can to directly infer the expansion rate today. Of course, with the caveat that we need calibrators and so on. So it's very hard to get to this direct measurement. And we can also infer the expansion history. So the content of dark energy and cold dark matter. And similar for the BAO measurement with galaxy surveys that I will talk about from Boston DBOS and DESI, which gives us the relationship, also a measurement of the Hubble expansion, the unnormalized Hubble expansion, and this product of the expansion in units of the sound horizon that I introduced before. Okay, to give it a bit more structure, although this is really simplistic now, I want to introduce some physical parameters, which I call capital alpha. It's not an A, it's capital alpha. And the model parameters, which I call omega, okay? So what are these things that we directly measure? For example, we have the spectrum of the CMB, which we can infer to get the temperature, the photon temperature, directly measured, with the black body spectrum. We have the CL, which give us this theta star and the fluctuations of the temperature, photon temperature across the sky. We have this BBN measurement, which gives us abundances of deuterium and helium, and we can use that to infer the baryon density. We have the brightness of supernovae, which we can use as standard candles, and this brightness is directly measured from the light curves, and we can use it to infer the Hubble constant. And we can directly use it to get the normalized expansion history. And finally, from BAO and EBOS DESI, we measure spectra. That's the raw data, and then we can reduce it into a map of galaxies, where we measure these oscillations and get this H0 RD, and also the expansion history. Sorry that there's a lot of information at once, but I want to really make this point that there are things that we can directly measure from the data and things that we infer using a model. Okay, so as I said, that's the composition of the universe. With Planck, we have measured this inflation parameters as well. We have this Hubble tangent, so we are not quite sure. Is it somewhere between 67 kilometer per second per megaparsec and 73 or so. And 95% is dark. And what are the inflation mechanisms that lead to that? So these are questions of the model that we still need to find an answer. And the dark energy spectroscopic instrument aims to shed light on all of these questions. So what's DESI exactly? It's serving the universe by mapping out nearby galaxies. And it's observed tens of millions of galaxies. But if we were measured each galaxy once at a time, it would take 20,000 years. So how does DESI do it with an army of 5,000 individually controlled robots? By the way, if you would like to know more about this, our DESI ambassador, Bao Ban, I've written a blog post about it. So if you're interested, you can check it out. It was drawn by Claire Lerman. We led the outreach committee. I was co-leading it last year. And yeah, it's a very nice, she also made this t-shirt, by the way. So let me tell you about the DESI focal plane. So is the plane of the 5,000 robots. They can all be individually controlled. They have fibers inside that can be targeted to galaxies. And within like exposures between, depending on the conditions, 3 minutes, 20 minutes, you can get the spectra to a resolution, I think, of 60, velocity of 60 kiloparsec. And we use it to obtain a map of galaxies. So 10 years of SDSS delivered 2.8 million galaxies, and already the first 6 months of DESI, 7.5 million galaxies. And we can use it to measure this BAO signal, use it as a standard ruler, and also learn something about the structural history with redshift-based distortions. So how exactly is the pro? Let's go step by step. Before we can measure the spectra of these galaxies, what we need to have is an imaging survey that has already images of billions of galaxies. So these are 2 billion objects observed by legacy imaging surveys on this 14,000 square degrees on the sky. Next, we need to select targets that we want to target and measure their spectroscopy. You can apply different certain criteria on the photometric bands to select those galaxies. And then we go from 2 billion to 50 million objects that we want to target in the end. Then we point the telescope into the sky. In one exposure, it measures the spectra of all these of 5,000 galaxies at once at a time. And then we tile the sky from night to night. We get new tiles on the sky. And this is the sky we had after 1 year of observation from the full 5 years of observation. So you see there's this on the equatorial plane. It's a very high, we have high density regions. And then here we also have measurements on a large volume. This is now roughly 7,000 square degrees. It differs from redshift to redshift, but that's what we have roughly for the first year of observation, DR1. And yeah, we measure the spectra. We know what's the rest frame spectra should look like. By using the spectral lines, we can infer what's the redshift. So how much have they receded, the galaxies, from us? Then we need to correct for systematic uncertainties. For example, this focal plane, the robots, they have a certain patrol radius. They cannot come too close together. So we are limited by certain radius that we cannot resolve below. And we have to take this into account in our measurements, either with weights or with something we call the theta cut method. And once we have this catalog, we have the 3-dimensional distribution of galaxies. And what we want to get from that is the summary, the clustering statistics. So what is that? Imagine you have the 3-dimensional map and you throw sticks into the sky with different lengths and angular direction. Okay, different lengths and different angles. And then you just count how many pairs of galaxies have exactly that separation and that angle. You make a histogram. We call that histogram psi of r, the distance, and the cosine of the angle. You can Fourier transform it and get the power spectrum, which depends on the wave vector and the angle. Then we also, for the BAO measurements, we do something that's called BAO reconstruction. So imagine you have a ring initially. Once you have gravitational collapse, the ring gets distorted, okay? And we can actually use the map itself to see where there are overdensities. These are regions where matter is falling inside, and we can reconstruct and try to put the galaxies into their initial positions. And that's something we call reconstruction, to recover that circular shape of the BAO. And what we get from that, so this is this histogram I was talking about. So here on the x-axis, there are different length scales. And you see at a certain length of 100 megaparsec over h, there's this bump, the BAO bump, which indicates this overabundance of pairs at that length, which are still left over of this bioacoustic oscillation that I talked before in the mesosoup and so on. So, and actually there is 2 lines. One is the pre before reconstruction, which is the dotted line, and one is the post after reconstruction, where you see that this peak is more pronounced. And these are the measurements from the DESI first year of observations in different redshift bins for different traces. The bright galaxy survey up to redshift 4, the luminous red galaxies up from redshift 0.4 to 1.1, the ERGs from 0.8 to 1.6, and the quasars from 0.8 to 2.1 in redshift. So, and these are the correlation function, and we can Fourier transform, make also a measurement of the quantity in Fourier space, which are the power spectra. And there in the power spectra, this isolated feature at one length becomes a spread feature. It becomes these oscillations that you see on this plot. And we can infer the BO in two ways, either analyzing this Fourier quantity, which has these wiggles, oscillations, or in the correlation function plot that I showed before, this one. Actually, and the DESI-1 analysis is based on these. Okay, so DESI-BO was obtained from the post-reconstruction of this quantity, and it shows the angular dependence. We have actually summarized it in a monopole component, which is the isotropic component, and a quadrupole component, which is an anisotropic component. And why do we have that anisotropic component? There are two things. First of all, there's the Alcock-Paczynski effect. When we use the redshift, when we put the galaxy redshifts into a grid, we need to transform the redshifts to a Cartesian coordinate system using a fiducial cosmology. And this distance this co-moving distance then depends on the angle under which we see the structure and the distance towards that angle. And we have two components, the perpendicular component and the parallel component, and they are sensitive to do different things. One is sensitive to the angular diameter distance, and the other one is sensitive to the expansion rate at that particular redshift. And if the fiducial cosmology is wrong, it's not corresponding to the truth, then we see that as an anisotropy in these measurements. The another source of anisotropy is redshift space distortion. So imagine we measure the galaxy. The galaxy is receding corresponding to the Hubble flow, and we interpret it as if it was receding corresponding to the Hubble flow. But in reality, the galaxy also has a peculiar velocity. It's not just still in co-moving coordinates. It's also moving along, right? And actually, the component that is parallel to the line of sight is misinterpreted. And so the galaxy appears at a position where it actually is not. And this leads to an anisotropy along the line of sight. And we call it, what we measured, the redshift space position. And it's displaced from its true real space position. And we need to take that into account into our models. So because of this effect, we have a squashing effect on large scales, which is proportional to the infall velocities of galaxies. And we can basically model it using predicting what should be the peculiar velocity of galaxies given the gravitational potential. And we call it the growth rate. And measuring the growth rate is we can basically use it to confirm our notion of how matter attracts, how the velocity is related to the gravitational potential. So it's a way of testing the theory of general relativity. And then we also have this finger of God effect. It's when there are virialized structures, you see it as a very elongated structure. So here you see this map where you have on the left-hand side the redshift space, where you see all these finger of God structures along the line of sight, whereas in real space it looks they are compressed and they are actually spherical virialized structures. So how do we model all of this? First, we start with the power spectrum template that we get from class. We need to assume that galaxies are bias tracers of the total matter density fluctuation. We only see the galaxies, we don't see the actual dark matter. So there are bias models accounting for that. We need to include the nonlinear corrections, like perturbation theory corrections to the theory. And then we need to include this redshift space distortion model and model that there is an anisotropy, which leads to the presence of a monopole and a quadrupole. And then there are different types of how we can fit to that data. In the BAO fit that I will talk about next, we only fit the residual part of the wiggles that you see on the left. And in the so-called full shape fit, we fit the data. We don't normalize it by the broadband. And we basically scale this power spectrum template and try to see at which scale do we match that oscillatory pattern. And here we also scale them and also vary this growth factor, which gives the amplitude between, or the ratio between the quadrupole and the monopole. And we also, for this analysis that is coming out soon, vary the shape of the power spectrum, the way that we suggested during my PhD thesis in this paper. But this is not the only way you can do. We could also, instead of having this template where you try to infer this, so when you infer these parameters, you can basically relate them to observables, which are the angular diameter distance and related to a fiduciary cosmology, and the Hubble expansion rate, and the growth rate, and the shape of the power spectrum. And then you can get these quantities and compare them to models. So there's an intermediate step. You have these alpha parameters, these observables first, that you measure first, and then you can infer cosmology from there. But what you can also do is that you don't care about these observable alphas and just directly fit the model to the actual data. Okay, that's what we call full modeling fit. And that's what is done to get all the cosmological constraints in the DESI papers that are coming out. So there will be two papers. One is doing this, and the other one is getting the alphas. Okay. So let me also briefly talk about these DESI behavioral results that came out in this April. So yeah, we also there. One of the Claire also made a cake that has this cover image on the side. It's really nice. And you could also see on the cake, it also had all these plots. So these are the correlation function BAO signals that were measured in all these different tracers of the galaxy types at different redshifts. And we can use it you can plot these measurements on the Hubble diagram. So these are these distances. And what we found out that it agrees well with the standard lambda CM model. There's a discrepancy between the best fit to that data with respect to what's given by Planck. Here you see the Planck prediction in the shaded region and the plus minus 1 sigma. And the best fit of the lambda CM model actually is a bit different, as you can see. And what we found that actually when we fit a model of varying dark energy, so the blue line is fitting a model of a different type of dark energy that varies its equation of states. So it's not a cosmological constant. It's a different alternative way of parameterizing dark energy. DESI alone preferred this blue line. And you see it's due to a combination of data points here. And when combining with CMB and year 5 supernova, you get this orange line. And so there's something there, but one must also say that it's only the first year of observation, and you've seen from the sky area, it's not yet the full footprint. So it might well be just a statistical fluctuation, and soon we will learn more about where this is going. So yeah, at the moment we had a slight preference for the parameter values of this dark energy that are different from the prediction by lambda CM, which is here, which still lies on that degeneracy, right? But when combined with different supernova samples, there's different levels of disagreement with that point. So yeah. I also wanted to quickly touch upon blinding. So all these measurements were blinded at the catalog level before we unblind and did the actual data analysis. And you might think, how is this related to accuracy? Because if you throw something blindly on a data, you are not supposed to be accurate. But anyway, this is not an accurate picture, right? Because what we do in cosmology is more this way. we're not doing ourselves an experiment. We are just letting the photons hit our telescope. So probably that's the more accurate way of seeing it. Anyway, so what we suggested, I introduced this retro space distortion signal. And what we did is we basically mimicked a different type of retro space distortion. So we changed the gravity law, and we shifted all the galaxies, acting as if the growth rate, the way how the gravitational potential is related to the velocity, changing that relationship. Okay, and that was one part of the blinding, and we also shifted the geometry of the universe in a coherent way to blind this BAO measurement. We actually proposed this already in 2019 in a collaboration meeting. Back then, yeah, it took a while, but in the end, so I wrote a paper on that during my PhD, and this was the blueprint for. So that's basically the idea that we put in the paper, that we have a blinded catalog of galaxies, and no, we have basically, before we unblind, we make sure that when there's new systematic weights, when there are changes in all different parts of the pipeline, we only look at the blind catalog and on mock catalogs before we actually freeze the pipeline and unblind for the final measurements. And yeah, so this was we suggested back in 2020. In 2024, this was there is a paper came out which we applied it to the actual DESI mocks and validated for the year 1 analysis. And there's also a blinding scheme for local primary non-gaussianity that I cannot touch upon yet, which is also implemented in DESI. And also for the bispectrum, this same catalog level blinding scheme was tested and works fine. So there's a lot of work going on now on catalog level blinding, which I'm quite happy about. So to conclude, because I think I'm almost at the time, right? A few minutes. So yeah, so the point I want to make is that with this blinding scheme, we enhance accuracy by mitigating confirmation bias to make sure that we do the analysis only on mock catalogs and we see the response change on the blind catalog before we actually unblind and say, now we are confident, and we apply to the catalog that doesn't have these shifts. And yeah, there are these small hints of the DR1BO results that hint towards evolving dark energy. So what to expect now? Soon, in a month or so, we will have these full shape results, which there will be one paper using the shape fit analysis, and it's more similar to the BAO kind of doing the analysis. So you have you get observables that are related to BAO, retro space distortion, and the shape of the power spectrum. And so these stand on their own. And then there's also a full modeling part where the actual parameter constraints on cosmological parameters are derived from. And I think it's really nice that in DESI we have both, because speaking from a philosophical point of view, we can, looking at these observables, it's more like of a data-driven approach where we see to which observables do the data actually drive us, without us having the need of making sense of how they should be linked in a model. And we can, so I would call it's like almost like more an induction approach, whereas the full modeling, it's a complete deduction approach. You start with the model, you calculate it all through and compare it to observable. As I've introduced earlier in the introduction, there are quantities that we can directly infer, and some quantities that we need the model to get through it. And having a compromise between the two and see whether we converge using these two approaches, I think that's a very nice way of leveraging this idea of precision versus accuracy. And yeah, let me add that beyond that, I also involved in the analysis of higher order statistics. So instead of looking at the power spectrum, which is pairs of galaxies, we also look at the bispectrum, which is triangles. So we look at how we basically count all the triangle configuration of galaxies, and also look at odd multipoles, which are introduced by relativistic effects. So this is also where where people from here are very involved in DESI. And yes, also the year 3 is coming soon, and there's more data to come. So really looking forward to what comes next. Thank you very much.
Questions?
Very nice. So full shape coming soon. So can you say something about not the accuracy, but the precision differences, full shape compared to BAO? Hello,
Yeah.
what can we expect in terms of improvement of mysterious?
Yeah. So I can give the exact numbers now. But so it's basically, rather than being more precise for the same quantity, it will deliver something that we did not measure with BAO alone, right? It will deliver the measurement of sigma A, which is the fluctuation amplitude, the overfluctuation amplitude. And with DESI, since we have the different tracers, we will measure sigma 8 at different redshifts. And with the combining all of these redshifts will lead to a precise value of this quantity sigma 8, and will shed more light on this sigma 8 tangent that I didn't discuss now, but which is also an important problem right now in cosmology. And yeah, it will deliver better precision than was done in predecessor experiments.
So in terms of W0 WA, the W0 WA plot, you expect similar mysterious?
Yeah, it will go beyond, because it will always combine. So it will be also cumulative measurements. So we will combine the BAO measurement that we have with the full shape measurement that we are doing right now. So there will be increased precision on that as well.
Allowed to do that?
Yeah, because we can model the covariance, right? It's yeah. Yes.
Will the full shape analysis be competitive in terms of 2D constraints in the neutrino mass?
Yes, yeah, as competitive as it was already. I mean, I didn't talk about the neutrino mass here. I don't know, I have it, but already the neutrino mass from BAO alone was very competitive, right? And that too. Yeah.
That uses only the expansion district.
Right. But also the CMB, where the CMB also includes lensing and growth part. Even the CMB without CMB lensing, without ACT or so on, is the lens power spectra. So lensing.
Yeah. I always thought all the constraints so far come from the constraints in expansion history.
Yeah, there are different views on that, right? So there was this paper by Dylan Green saying that actually it's the lensing part which dominates. Now there's a paper by Marilena Loverde saying that it's the geometry. When I was in the Neutrinos from Home conference, I tended towards the latter. But yeah, it's very involved. Yeah.
But I haven't seen any paper that takes that you can really see the expression of matter that scale and not overall.
Yeah, right. That's yeah, there will be something about that is coming out, but yeah, because that's really something we can only measure from growth and not from geometry.
Questions?
Yes.
So assume that you combine analysis with shape fit and full shape, and you find that the relevant cosmological parameters are like different
Yeah.
from the two approaches.
Yeah.
So what would be the first thing you think? Like what would you trust more? Or like where do you think that's some problem? in the interpretation approaches.
Yeah, I would. The first thing is, I would think, can we come up with a model that would reconcile this discrepancy? But also, maybe, is there something in some systematic ingredient that we haven't, where we're not aware of, and maybe we have to look at it more carefully. Doing blinding doesn't mean that you can, when you unblind, you have to live with the result and publish it. You can also go back and make transparent the papers. Oh, there was something that we adapted after unblinding. So yeah.
No, the question was not
Yeah.
about unblinding,
Yeah.
more about like the different approaches.
Yeah.
Shape fit. And with shape fits, I mean, you don't really fit the cosmological parameters of your model directly, but on some parameters that you infer from the data, right?
Yeah, exactly. Yeah, I mean, it would be interesting if you see there's a discrepancy between what this approach gives and the direct modeling approach. I think that would be very interesting, because you would need to dig into it more and try to uncover where this discrepancy is coming from. Yeah.
Questions? Just maybe I will ask the last question. Do you expect anything new from the primordial non-Gaussianity side? Because 1 year ago there was this paper that found the value that does not agree with Planck.
You mean the paper that was applied to the DESI legacy imaging, the photometry?
Probably,
DESI.
yes.
Yes. Yes. So this is also ongoing in DESI. And so yeah, it will be very interesting, especially to see what is the added value of having this full spectroscopy rather than only the photometry. So yeah, will be very interesting.
There is also a question online by Veronica. Maybe can you use the
Yes, I can see the chat.
Yeah, can you hear me?
Yes.
So I can ask it like that. I'm wondering, do you have an example for attention without a model? I can't really wrap my head around how you can get attention parameters without assuming a model.
Yeah. So, for example, you could, this is related to this last sentence I have here, which you can have tangents within the model, but you could also have tangents when you don't assume a model, but you have observables that don't agree with each other. So, for example, supernovae, you can measure the unnormalized expansion rate of the universe, right? With Pantheon or DES, of course, we have the problem that different supernova samples, they have kind of a disagreement there. So I think there's something going on that needs to be uncovered there. But now imagine that BAO would also measures the h of z divided by h naught. And there's a discrepancy in that measurement with supernova. So when you see a tangent before you actually introduce a model itself, I think that's that really seems like there's something fundamental that needs to be looked at. And that's why I say here, it's interesting to consider that type of tangent, because within a model, you can just generalize the model, and then you can be. I don't say that it's easy to accommodate the Hubble tangent, for example, just changing the model a bit. But I think the point is that when you see that there's something discrepant at the observable level, then that really means that there's something we have to figure out before even thinking about the model. It might be systematic uncertainties, but I think that's why it's intriguing to look also at these observable alpha.
Right, thank you.
Not less thank the speaker.
Thank you.
People that are joining for lunch, we meet at 12:15 at the entrance.